You're watching the 4.6 geometric sequences and more recursions video notes. If we rewind, take a trip down memory lane, we've already talked about arithmetic sequences, and that was in the linear functions unit, because if you remember correctly, we were adding something over and over and over again. Well, you probably are going to make the connection now with geometric sequences. Since they're in the exponential functions unit, we are probably going to now have a yes multiplier. You are correct. The hardest part about this stuff, which isn't hard at all, is just trying to understand that weird notation. The math was super easy, but the notation is where we have to be careful. All right, so exercise 1. Hey, we've seen this question before, haven't we? This was like the first day. So we were counting up the number of black triangles, and figure 1 we had 3, figure 2, oops, that got all weird. So figure 1 we had 3, figure 2 we had 9, figure 3 we would have 1, 2, 3. Oh my goodness, I don't want to do all that, but I think that if we did end up counting all of those, we would end up with 27. And then in figure 4 we would have ended up with 81, and if there was a figure 5 on our paper, we would have 243. How am I figuring that out? Well, we're realizing that every single figure we're tripling. So we have a multiplier going on, don't we? Over and over and over again. So if I wanted to write this in that weird before, now, next lingo, which we visited in Unit 3, what is happening? Well, in order to get to the now, didn't we look before it in the table? And if we look before it in the table, I think we have a multiplier. What is that multiplier? Yes, it's times 3. Okay, now when we write it as a function, we always need to find the y-intercept, which is hiding in our table. So how are we going to get that y-intercept? Yes, divide by 3. So we're just following that pattern backwards. 3 divided by 3 is 1. So in order to get a function, in this case it's b of f, we're going to be careful with our notation. We have our y-intercept, our starting value of 1, and that's being multiplied by 3 over and over and over and over and over again. I could do this, but that's not a function. So instead what we're going to do is model that repeated multiplication with, an exponent. In this case, it's to the f power. Okay? Now, D says explain what the input of 1.5 would mean in the context of the problem. So that's really, okay, what are we talking about? They want to know what 1.5 means here. Okay, so that would mean, wait a second, isn't that my figure? So it would mean 1.5 figures, or a 1.5 figure, or figure 1.5. What? That doesn't make sense, does it? Let's write that down. Sense. What, did I spell sense wrong? S-E-N-S-E. What is going on in my brain today? You know how sometimes you write words and then they look weird? That's how, I don't, okay. Sorry if that's spelled wrong. I think it's spelled right now. Okay. So write this pattern using a recursive formula. Recursive formula. Oh, this is tricky. Tricky, tricky, tricky. All right. So if I want to figure out a recursive formula, this is a little advanced, maybe something that we're going to revisit again in the future. But the reason why we're going to have to do some type of recursive pattern is because we're looking at a geometric sequence. For the explanation that we just talked about in D, it doesn't make sense to have halves of figures. So we are not connecting our points if we were to plot this on a graph. Just like with an arithmetic sequence, we didn't plot the points. Like we wouldn't want to have half of a frog or half of a fish. We would either have 1 fish, 2 fish, red fish, blue fish, or 3 fish, 4 fish. We cannot have parts of the item that is in a geometric or an arithmetic sequence. So if we want to write it as a recursive formula, we want to get b of f. So what does that mean? We're going to look at the term before it, so b of f minus 1. Remember that weird notation, the f minus 1 and f plus 1? And then we're going to multiply that times 3. We could also put the 3 out in front here and do 3 times that. But something that's really important when you are talking about a recursive formula is that you also have to say where to begin, right? So the first term or the first figure has 3 triangles. With the recursive formula, if you don't have a starting point, you can't do the problem. So this here is something that people leave off a lot of times, but that's like the most important part of the problem because otherwise you can't do the thing. All right, so that multiplier is what we call a common ratio. So if you ever hear that lingo, that's just the multiplier. All right, so exercise 2 says find f of 5 given, You know what, guys? Let's not do this one. I'm going to skip this. We're going to revisit this in I think unit 7. We're going to revisit this type of notation in unit 7. All right, let's skip to the next page. I hope Mrs. Hayes is okay with this too. I'm making an executive decision. Ooh, we can do number 3 though. All right, in a geometric sequence, the first term is, 1,536, and the second term is 384. What is the 5th term? Do you guys remember? Sometimes it's easy to make a table. The first question exercise that we had, the table was already there for us. Here, it's not. So let's say our first term or our term number is our x, and the actual term is our y. So the first term is 1,536. The second term is 384. Oh, it's going down. They want us to find the 5th term. So if we can get this number here, we have done our job. Well, I'm a little confused about this. So how can I get that multiplier? Well, if I want to get my multiplier, I can go backwards and divide. So I can divide 384 by 1,536. So if we bust out our calculators, I don't have mine on the screen right now. You know, I'm going to do it on the calculator that I literally have sitting next to me. You should do the same with your handy dandy Nspires. When I do that, I divide and it gives me 1/4. So if you take out your calculators and do 1,536 times 1/4, the magic, can you hear my calculator clicking? I got 384. So my multiplier is 1/4. So if I just take that 384 and I continue to multiply that by the 1/4, or some of you might say, can I write it as 0.25? And the answer is sure, why not? What are you going to get? Well, so 384 times 0.25 is 96. And then 96 times that 0.25 is going to give us 24. And that 24 times the 1/4, or 0.25, will give us 6. We're just multiplying by 1/4 every single time. So the 5th term is 6. All right, I'm skipping exercise 4 because, again, we're going to revisit this in unit 7. In exercise 5, one of the following sequences is arithmetic and one is geometric. Ooh, we get to compare them. This is interesting. Okay, so arithmetic means I'm going to add. Geometric means multiply. All right, so let's look at sequence number 1. Sequence number 1, how am I getting from 4 to 8, 8 to 16, 16 to 32, 32 to 64? Oh, I think I'm adding 4, right? So plus 4, 4 plus 4 is 8, 8 plus 4 is 12. Uh-oh. I smell a multiplier here. All right, let's try that instead. 4 times what is 8? Oh, 4 times 2 is 8. 8 times... there it is. Times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. Okay, this has a multiplier, so this is geometric. Because we're multiplying. All right, says to write a recursive rule in function notation that models the sequence. All right, we got this. It doesn't give us like f of x or any of that, so we get to pick. I am going to just use f of n then. Or you know what, let's use a sub n. We haven't used that in a while. So a sub n is going to equal my before, which would be a sub n minus 1, and then it would be 2 times that. So 2 times that. And we're done, right? Wrong. You are right. We have to say what the first term is. So the first starting value is 4. And I don't know why my screen is frozen. Let's see if I can get down. Here we go. Is 4. All right, let's look at this sequence 2. All right, well, what's going on here? How do I get from 4 to 8, 8 to 12, 12 to 16? Oh, this is what we wanted to do before, isn't it? Adding 4 over and over again. So this is arithmetic, and I always spell it wrong, so what is it? Okay. This is arithmetic. I'm spelling this wrong again. I thought I knew how to spell it. M-E-T-I-C. All right. There we go. And we know it's arithmetic because, my computer is freaking out, because we are adding. Okay. And then write a recursive rule in function notation. All right, so let's use that a sub n notation again. So a sub n is going to equal, all right, my before, so a sub n minus 1, and then what were we doing? Yep, we were adding 4. You got it. And then we're done. No, we're not. You are right. We have to say our starting point. What is our first term? Oh, this one was also 4.